Good morning, folks. Or actually, I guess for a lot of us joining today, this is good evening. I'm Carol Urbano, and I'm the program coordinator for the Nord Anglia program here at the MIT Museum. And we're joined today by my colleagues Amy Gillespie and Rahi Patel, who will be helping us manage some content in the chat and the Q&A. And I'm also joined by um, Kim Arcand. Lucky for us, she has a queasy stomach and was never able to reach her lifelong dream of becoming an astronaut, but instead pursued the stars in another way that we're going to learn about this morning as a data visualization scientist. And I'm going to hand it over to Kim. Good morning, Kim.
Good morning, everybody. Thanks so much for having me, and I hope you'll enjoy what I have to say. It's very early morning for me, so if I stumble over my words, you'll have to forgive me. I'm just going to share my screen and bring up some slides to take a look at. And here we go. Hopefully everyone can see that. So I'm going to talk a little bit how I get to walk among the stars, even though I can't visit the stars myself. For me, it's all about being able to access data out in the universe down from here, happily comfortable on Earth. So my job is essentially being a visualization scientist, and I also am the emerging technology lead for NASA's Chandra Xray Observatory. That's a whole lot of words, which essentially means that I get to play with data all day and get paid for it and look at images of our universe and help make models. And it's just a really fun thing to be able to do. However, this is actually what I started out doing. I did my undergraduate work in parasitic and infectious disease underneath the umbrella of molecular biology, which is, I guess, timely for these days. And what I realized is I was using the microscope a lot, of course, for that type of work, and I had done a lot of science. But what I actually really enjoyed the most was using computers to sort of figure out how to work with that science. So that for me was just really exciting to be able to see that I could have a career path that was something besides what I did my undergraduate work in. So I stopped looking at ticks, used essentially code, learned how to code in a couple different languages, and taught myself how to be able to work with data of different kinds. And that brought me to here, working for NASA's Chandra Xray Observatory. I actually started working for Chandra back in 1998. So it's been a while, and my job has changed tremendously over that time, which has also been, I think, a really fun thing to be able to experience. So what Chandra gets to do, essentially, Chandra goes about a third of the way to the moon. It's observing our universe in X-rays, which it has to do from up above Earth's atmosphere, because one of the superpowers of our atmosphere is that it protects us, humans down here and other kinds of life in general, from the really harsh X-rays from space. So Chandra operates above that protective layer so that it can see clearly out into the X-ray universe and make those observations and record them on its device. So what does Chandra get to look at? It gets to look at things like exploding stars, areas around black holes, colliding galaxies, and a whole lot more. So some pretty exciting and energetic events that are happening out in the universe at any given time. I'm going to give you a very, very brief mini tour about some of the images and data that we get to collect and look at and create. This is a bunch of baby stars, essentially, stars in the process of being formed. It's called the Pillars of Creation. This is another collection of young stars, a little star cluster called NGC 602. This is a mature star, Eta Carina, that may or may not explode in our lifetimes, give or take like 500 or 1,000 years. This is a star that's already died. It's G299.2-2.9, which is a very exciting name. But you can see it's this sort of gorgeous looking cosmic flower, and it's the remains of a star that exploded. This is another dead star. This one's called the Crab Nebula, and inside its core is a little bit of the leftovers from the star that exploded, and it's a very compact, super, super dense material. If you took like a teaspoon of it, or if you took like a thimble and actually shoved all the entire population of the world into that thimble, that would be about as much as what's inside that core in a thimbleful of it, which is pretty incredible to think of how incredibly compact these objects are. And this is a beautiful galaxy that we're looking at. Chandra gets to look at galaxies of all shapes and sizes, galaxies that are merging, galaxies that are colliding, galaxies with supermassive black holes buried at their center, clusters of galaxies, which are the largest gravitationally bound objects in the universe, and clusters of galaxies that look like they're smiling back at us. So this is my hello, everybody, brief smile to everybody out there that might be watching. So my job essentially is, as I mentioned, working with data. You might know that this is what we're looking at here is just a bunch of binary code. Binary code is a system of ones and zeros, which are like having ons and offs. And it's a way to essentially talk to spacecraft. It's a way that we talk to our cell phones. It's a way that we talk to all different kinds of computer and electronic devices because of that simple system of on and off, just like electricals work. So the Chandra Observatory, how it operates is there is this object in the universe. Light has been emitted from that object and it's been traveling for some time. Chandra is looking at that object and observing it at a specific moment in time here, and that information then makes its way down through the telescope down to the scientific instruments. It's recorded and it's packaged up in the form of ones and zeros before that data is then transmitted to Earth, and eventually it makes its way to our laptops, wherever we might be. At first, it might not look super exciting. It's a table of data that we get that we then have to do something else with, right? So we have to use software and various layers of coding to essentially make something with that data to create an image like you're seeing here. But even once we have images, you can see that one big thing is missing. After we've done scaling and cropping and different kinds of artifact removal, we still have to add color. I think what's important to think about when you're looking at any type of image of space, especially deep space images, is that pretty much any of those images are going to be color added images, because most of the telescopes and spacecraft that we're using to look at these objects, they're looking at objects that are both very far away, and also they're looking at them in different kinds of light than what human eyes can see. So for example, if you think of a keyboard, a piano keyboard, and if you think of the amount of light that we see out in the universe, it'd be like the equivalent to middle C and a couple keys on either side, and that's it. All the rest of the keys on that keyboard, those would be all different kinds of light. So if you're at all like into playing piano, think of how your favorite piece on the piano might sound if you just had middle C and like 3 or 4 other keys. It's going to be a little boring. At least I'm pretty sure it's going to be a little boring. The same thing if you think of like a ball field. If you could only see a very tiny sliver of, say, a soccer field or a football field or a baseball field or a cricket field, whatever it might be, if you only had a very tiny, tiny portion of that screen that you could access, you would lose a lot of information in the universe. So fortunately, scientists have learned ways to be able to see the entire universe across the electromagnetic spectrum, to be able to understand more of what's going on out there. So when we add color to our data, especially in X-ray astronomy, it's because we cannot see any of these objects with human eyes ever. So those colors, human eye understanding colors, they don't exist. We have to add color to the data in order to add to the information quotient in order to make sense of what it is that we're looking at. So we're looking at one of my favorite objects here. It's Cassiopeia A, and I think probably some of you have watched one of my previous talks where I wax very poetic about this object. So Cassiopeia A was essentially a star many times the size of our sun, at least 10, perhaps 15. It got old, it ran out of fuel, its core collapsed, and then it exploded all over the place. And that explosion, those leftovers, that essentially forms what's called the supernova remnant. So here you're looking at this beautiful stellar death, this beautiful debris left over from when that star exploded. And you can learn a lot about how stars explode and about where that material goes and what it does by looking at how stars explode. I think a good way to think about it is we can't look inside stars when they're, quote, alive, right? When they're just normal functioning stars. So when you see a star explode, or when you're looking at the aftermath of a star that's exploding, it's actually a really great way to understand what was inside that star and how that star functioned before it died. So it's kind of like being, a Sherlock Holmes. So when you have a lot of really good data of an object like Cassiopeia A, you can essentially create what's called a 3D model. And in this case, we use data from the Chandra Observatory, but also from the Spitzer Space Telescope and some ground-based optical observatories. So we're using all different kinds of light and patching it together into one model, and it helps us essentially figure out what this object is like and how it exploded and what happened during the explosion. And you can see in this 3D model that I had on my screen, I think play the video one more time. The green portions around the edges, that's iron, right? And so iron is actually in the innermost core of a star before it explodes. But here you can see that much of the iron, if not most of the iron, is along the perimeter. So what does that mean? That means a star like Cassiopeia A, when it explodes, it turns itself inside out, quite literally. So being able to see it distributed like this in a 3D model is actually really helpful. So this is a 3D print that we've created of this object. This is done in 3-color using a special powder printing format. And what that allows us to do is have a physical model of that object, but then preserve the color information. And I have a version of Cassiopeia A here. You can see on my screen, this is just a 1-color version that I've made using an Ultimaker type of 3D printer. You can see the difference. It's nice to be able to preserve the color information, so you can still see, for example, on the one on my screen, that green is the iron. So another thing that we've done more recently is we've taken that same 3D model and brought it into virtual reality space. This came about kind of accidentally because I was working with a student group and we were doing tours of a 3D lab, and the lab manager had brought up 3D data of Mars. And so I was able to walk on Mars. And I can tell you, as someone who will never venture into space, that was a really fun and cool thing to do. I've been looking at data of Mars for years. So to be able to walk on it was just a very fascinating experience. And I thought, well, I have 3D data. Can we bring that 3D data into virtual reality space? And so we created this program with Brown University to essentially do just that. And we've been taking our models, once we have 3D models in some form, right, bringing them into virtual reality so that we can walk inside them. So you're seeing one of our students there. She was walking inside that dead star. The camera person was outside, so it's hard to tell, but she's actually inside, walking around inside this star that exploded 10,000 light years away from us, and she's able to understand it and question it from inside. We've also brought it into augmented reality so that it can be used in office spaces and school spaces as well. We're developing a special phone application so that pretty much anyone with a phone can do a type of augmented reality application where you are essentially building this supernova remnant. You're putting in all the ingredients and you're telling it to add the iron, add the sulfur, add the silicon, and I think that's a pretty fun experience to have. So all of those things that I've showed you, that's all just from this data, these streams of ones and zeros that we get, that humans then do things to in order to create those visualizations, to create something, to make meaning of the data, to add value to the data. Because you can have a pile of data sitting in an archive that has potential value, but when you visualize it, when you understand it, when you analyze it, you're essentially adding value to that data. I'm just going to show really quickly one more example. Cassiopeia A is my favorite, but we've done this type of work now with other types of objects as well. This is another supernova remnant, an additional star that blew itself to bits, and this is called Tycho's supernova remnant, which was seen from Earth in the 1500s. And again, when you have fantastic data from a telescope like Chandra that's been operating for 20 years, it gives you a lot to work with. And then when you combine that with other types of data across the electromagnetic spectrum, adding infrared, adding optical, adding ultraviolet light, whatever the case might be, it just lets you see more of the picture. So again, with that, you've seen on my screen so far our sort of transition from 2D image into 2D image with more data, and now you're seeing the 3D model up on the screen, hopefully, and you're seeing essentially two pieces. And I'll show you the 3D print is in the next screen. So that's a version of it being printed. Here's a copy of it in my hands right here. So we have essentially the shock and the ejecta as two different pieces, which then they can kind of fit together. So you can see how those work. And there's just a quick picture of what I just showed on the screen. And similarly for Tycho, with all of our 3D models, we're working on ways to bring them into a virtual reality or augmented reality, what we call extended reality space, so that these materials can be used in a host of different ways, both for experts and non-experts as well. So that's the type of work that I get to do.
I have one question for you about the AR. Someone was asking whether or not that
Sure.
app will be made available to the general public.
So this one is right now, the one on my screen that shows Tycho. We also have the app that's in progress for Cassiopeia A that will be available, I'd say probably in a few months. We've been slowed down a little bit with the coronavirus issues. It's definitely taken a bit of a toll on some of our projects. But hopefully within a few months we'll have something on a phone version. But in the meantime, you can use your phone to access this virtual reality version of Tycho Supernova Remnants. And I will bring up a page in a minute, hold on, where you can access, there it is. So down here, chandra.si.edu/VR, that has access to all of these extended reality projects that I've been talking about. So virtual reality, augmented reality, we even have been working with some hologram technology to create holograms of exploded stars and other kinds of objects. So please do check that out if you're at all interested. I thought I'd go to questions pretty soon, but just wanted to pop up some resources in case anyone's interested in doing more. I talked briefly about binary code, and we have a very simple activity where you can essentially write your name in binary code. So you just go to the chart and you write your name or some like little message in binary code. And then you can also do the same thing and create like binary bracelets or binary pins by using like one color for the ones and another color for the zeros. And you can do like a number of fun crafting projects through that. We have a coding activity that essentially does what I do for my day job at chandra.si.edu/code, and it takes you through actual NASA data sets to be able to work with them to add color and do compositing so that you can see how that works yourself. If you're interested in some of the dimensionality that I've talked about, we have a sort of intro in this origami activity, which is chandra.si.edu/origami. And then we actually have a full 3D application that you can do online, all free, chandra.si.edu/tinkercad. And that actually takes you through the basics of how to 3D model. And then at the end, lets you bring in one of our actual models for Supernova 1987A, which I didn't yet talk about, but it's this gorgeous one right here. And you can actually work with that real NASA data to create your own 3D models. So I thought from here I would go to questions, and let me go over to the document, unless anything else came up in chat while I was talking.
Yeah, there have been a lot of questions coming up in the Q&A module, Kim, and I'm going to give folks to kind of upvote some of these while you
smart, great.
while you take some time and address some of the student questions that had come in over the past several days.
Great. All right. So I'm looking at this document of questions, and I'm just going to go through and pick a bunch. So the first question is that a group of students have been working in diagrams of cell models where we've talked about how colors are added to make it easier to understand, but that they're not actually there. So to what extent is it more informative or more misleading to add false color to scientific data? And this is a great question. And actually, maybe I will show my screen over here. Are you all still seeing my screen? Yes, okay, great. So this image right here, this is essentially it's a supermassive black hole at the center of a galaxy that's in a larger cluster of galaxies. And the supermassive black hole is very active, and it's just bursting out these jets, and there's this really hot, energetic material that's coming out of this object. So when we started working with this data, the first version of the image that we created looked like this. It's this blue version. So the blue is the X-ray. That's that superheated material that we're looking at. And the red area is actually these like cooler radio lobes. So data from a radio telescope that's been composited with it. So when we were trying to talk about the point of this story, however, it was very difficult to get across the idea that this is a superheated, super hot object in space when you're looking at it and you're seeing it in blue. The reason that we put it in blue is that in physics, right, blue is hot. So if you're looking at a fire, for example, the whitish blue part of the fire, or the flame, is actually going to be the hottest part, whereas the red part is cooler. So even though red to us means hot in a typical everyday sense, in physics, it's really the blue and the whites that are the hottest or the most energetic. So we have a way of color coding our data that gets across the point of physics. But when you're talking about an object and making the very specific point, that this is a superheated object, we thought that this version of the data actually made more sense because you understand that this is a superheated object much faster without having to even get very far in the text than when you're looking at something that kind of looks like, I don't know, like an iceberg when you're looking at it in blue. So we ended up going with the red version. So the point here, though, is that you really have to both know, A, what the science is that you're trying to communicate, and B, who is the audience that you're trying to communicate that science with. And those two cannot operate apart from each other. So you can make all of the images that you want, but if you're not understanding the science that you're trying to convey, and then if you're not taking into account who is actually going to work with that data or look at that data, understand that data, or whatnot, you're really doing yourself and everybody else a disservice. So the point is, going back to the issue of false color, when you have an image that, especially the type of data that we're working with that cannot be seen in human understanding of vision, that you have to translate into a form that humans can perceive, that humans can see and understand. You have to be able to understand what it is people are going to take away from your data and how it is that they will understand what it is you're trying to talk about. So, for example, you can think of it like a weather map on a weather app on your phone or on the nightly news, right? You're color coding those weather maps typically to show something, whether it's wind speed or whether it's temperature or the amount of precipitation, for example, whatever it might be, your color coding is trying to convey that information. And it's the same thing with what we call representative color in scientific imaging. I don't really like using the term false color because I feel like it makes it seem like you're doing something nefarious or weird right from the get-go. So representative color is what we typically call it because it's a way to take something that is not visible to the human eye and represent it in a way that is. But then as you're doing that representation, you're making sure that the data, the science is being told in a correct way and that the data will hopefully be understandable for your audience. But the point of all of this is that when you are doing that, you want to make sure you describe what it is that's been done and why, because you don't want people just feeling like they've been tricked or that you're trying to like pull one over on them. The point is really to be able to share something and tell a story about what that data means. So I really liked that question, and the teacher had provided some sample student work, by the way, which I thought was fantastic. So major thumbs up to Jack Cooper's class, it looks like. All right, so I'm going to pop down. Oh, there's another set of questions from Nord Anglia International School, Hong Kong. Let me go over to that window. So, all right, so it's just a 3D print. You won't be holding a dead star. Isn't it just a 3D print? No offense. No offense taken. I love questions of any kind. So no, I'm not going to take offense. No worries. So what this means is, so we are, for example, with the objects I've talked about very quickly today, for example, Cassiopeia A, this object is 10,000 light years away. This object is also incredibly huge. You could take the entire solar system and you're still nowhere near it. Cassiopeia A, its surface area is about maybe 40 million billion times the surface area of our sun, and you can add all the planets and you can add Pluto too if you like. I mean, that's how much more massive this object is. And 10,000 light years, though it's in our galaxy and it's close cosmically speaking, in human terms, it's rather far away. We don't have any chance of going to see this thing anytime soon. So for me, the ability to take something that's so nebulous, ooh, pun intended, that's so, kind of out there and abstract, and create something that you can hold in your hand is exciting for two reasons. One, it actually showed me in my job that there was a new avenue to explore. At the time, I got this idea on 3D printing from some friends of mine that had just 3D scanned and then 3D printed President Obama's head. And I thought, well, if they could do that, we should be able to figure out how to do this for a supernova remnant. And so when we were able to do that and hold a version of Cassie in our hand, you can actually learn something about it when you create a new version, when you're learning from or of an object in a different way using a different, what we call modality, right? So the sense of touch is different from the sense of sight. When you can hold something in your hand, you're understanding in a different way than when you're just looking at something on a screen. But to me, the most important thing that came out of this idea, this random idea, this bit of play that I was able to do in my job was that it ended up launching an entire new program for people who are blind and visually impaired. Because for someone who's blind and visually impaired, they can be left out of a visual science like astronomy, right? This is a very, very visual heavy field. And people who are blind or impaired have to figure out different ways to be able to learn about and access that data. Whereas somebody who is sighted does not have to do extra work in order to access this data that we all have the ability here to do in some form. So for me, it was fantastic to be able to take these and work with students. For here, it was at the National Federation of the Blind in the US, and the students actually helped me improve the models, helped us improve these 3D prints, kind of told us what makes it work better for them and what makes them easier to understand. And we actually wrote up a whole paper about it and ended up going on to create an entire kit of these 3D models so that now someone who is blind or visually impaired can access data of our universe just like somebody who is sighted. And that was an eye-opening experience for me, just because something that I just thought would be fun ended up turning into a project that I'm deeply, deeply in love with. And that has been probably one of the highlights of my career. And I've been working now for over 20 years. So that is the long story of this one. I feel like I'm going to get through like hardly any questions of the length of time I'm taking to answer some of them. I'll try to go a little faster. All right. So
I'm actually going to ask one that's from the Q&A, Kim.
Sure.
It's tangentially related to the question you just answered. But I know that in your work, you talk a lot about 3D printing and computer science. This is from Darren in Hong Kong. And he's wondering how important you think things like 3D printing and a thorough understanding of computer science are to actually discovery in science.
Yeah, that's a great question. So for me, this is such a brand new area. I can't definitively answer that, but I can say there are a number of papers that other scientists are publishing that actually do use 3D modeling in order to make the discoveries. So for me, at this point, things like 3D printing and virtual reality are still kind of being seen as one endpoint to the data. So you have data, you're able to do some things with it, you do make something with it, and you might make a 3D print or you might make virtual reality. And typically that's being done more often towards the end of the scientific process, right? So after the data has been analyzed in some way. However, these are still new and emerging technologies, and this is still a very new area. So I think it's just too early to say exactly what will happen, but I have a sense that it will become more important, particularly virtual and augmented reality. Virtual reality or augmented reality or any kind of extended reality that you can do in more real time, I think will be really important to the scientific process once we get our technology and software up to speed a little bit more. So right now, for example, there are a few different research groups in astrophysics that are modeling things like exploding stars, and they're modeling them right into a virtual reality pipeline so that they can be exploring that data with another scientist or user at the same time, which, when you consider the environment that we're in right now with coronavirus and inability to travel, could be a very, very powerful tool to be able to work with researchers that are spread across the globe in a way that is more like natural to how scientists typically work, which is very highly collaborative, right? the whole process of science is not some one person sitting in a room having a light bulb moment, doing something awesome. It is a very big team effort, lots of meetings, lots of just sitting down, talking to people, working things out. And the processes of being able to work through some of that understanding and analysis in real time with someone while you're both looking at a 3D model of something at the same time, whether it's an exploded star or galaxy or whatever, I think will be very, very powerful in the years to come. It is soon to predict it, but I think based on what I've seen so far coming out of the papers that it might take us by surprise quite a bit. And for sure, all of the 3D models that we've been talking about today and all of the other ones that I've been involved with at some frame, the 3D model is not created to make something cool. The 3D model is actually created to understand the science better. It's really about when you're looking up at the universe, right? We're looking from here on Earth, and we are looking up onto essentially what seems like a flat projection on the sky. So these images that we come down, that like the one on my screen, for example, that showed NGC 4696 is just a two-dimensional image. So being able to understand that these objects are not flat two-dimensional images, right? These are three-dimensional objects. So being able to understand an object in its more natural or native environment is incredibly useful for scientists. It's easier to be able to navigate through a 3D space, right? Which humans are very used to than just a slice or just a single viewpoint that we might get from here on Earth. So yeah, long answer, but I would just say I'm actually incredibly excited to see where this goes, particularly as new telescopes come online that collect better 3D data easier and faster. Do we want to take any more of those questions, Carol, or do you want me to go back to my list?
Sorry,
Carol's muted, so I will just continue. Okay.
The most popular question is actually, given the fact that Cas A is so far away from Earth, folks are wondering, what is the contribution that your research has to just our understanding, or how does that really impact us?
Well, I would say in general, the understanding of Cassiopeia A is the fact that anytime you have an exploded star, when a star explodes, all of the material inside that star, right, is being distributed out into the universe. So the iron, the silicon, the calcium, the sulfur, those chemical elements that are created in the furnaces of stars, and some that are created when the star actually explodes, like that material is the necessary material for life as we know it. So the literal calcium in our bones, the literal iron in our blood, those chemical elements come from, the only way they come from, we get them essentially is from previous generations of stars that exploded. So the stars that would make up us humans now were exploded a long time ago, but when a star explodes, that material essentially sweeps out into the universe and then is eventually swept up to form new generations of stars, of planets, of people. So that type of cosmic recycling is important for the very essence of life. So when we're learning about something like Cassiopeia A that's 10,000 light years away, we're actually learning a little bit about ourselves. When we're learning about something out there, it's telling us something about us down here. And I think that's actually a really powerful tool. I'd also say one other thing that I do like to talk about that I didn't put in my talk is that it's really hard to do these things, right? It's really hard to understand these objects that are so far away from us and to create 3D models and do whatever types of 3D outputs that we want. But the technologies that we've developed as humans in order to do those hard things are then incredibly useful when you turn them back around and use them here on Earth. Those technologies can be incorporated in incredibly exciting ways that for us have shown just the value that these difficult science research projects can bring us. So, for example, in any given day, my life is impacted by the very telescope that I work for. And I have to say, by the way, I went like almost 20 years before I knew any of this. But some of the technology that went into building the telescope that I work for now and previous generations of X-ray telescopes that had to get us to where we are, those technologies if I'm going to the doctor at any given point, different kinds of medical diagnostics are used or were created because of the technologies that built telescopes like Chandra. So whether that's some kind of MRI, whether it's mammograms, whether it's some kind of digital dental x-rays, there are all of these activities that have either been created or improved because of telescopes like Chandra and other similar telescopes. So I like to add that just as a piece because yes, we learn about things far away, and yes, that helps us learn about ourselves, but also on a daily basis, the way our food is put through quality assurance, the way that our equipment is scanned at, say, an airport or getting into a building, the way that our medical diagnostics are done, the way that our environmental scanning is done. Those technologies are due to many different advances that were made in X-ray astronomy and other astronomies around the world. So I always find that as a pretty exciting piece to learn about. So I see that there's one question here that's probably one of my favorite questions. This is from Gia, and it says, do you think that aliens exist? And I love talking about aliens. I think it's a great question, and I get this question from all ages, and I like to take a little time to answer it. Though it doesn't have much to do with Cassie, I guess we could sort of extrapolate on the possible formation of life that we were just talking about from supernova remnants, these recycling centers out there in the universe. And I would have to say that coming from a biology and my background being in biology from an undergrad, I love talking about things like the potential for life elsewhere. There is this entire field of study called astrobiology that wasn't even really a thing when I was coming out of grad school that I find just really fascinating because it's very difficult to answer these questions from where we are here in our universe, right? We live in the Milky Way galaxy. We're near our middle-aged star, the sun. We're on one little arm of the Milky Way galaxy. Our galaxy is just kind of an average spiral galaxy in the universe, kind of nothing, super exciting about that in and of itself. But when we look at all that we've learned in the past, say, 2 decades, we have found all of these exoplanets, for example, so planets outside our solar system. And every new exoplanet that's discovered, there's some fascinating thing about them, whether it has 2 stars or 20 moons, whether it's a frozen world or a superheated world where you would like poof into smoke in 2 seconds. Some of these worlds, it rains glass sideways. Some of these worlds, it rains rubies and sapphires. Some of these worlds are zombie worlds around dead stars. It's incredible to look at the differences that exist. It's just like a cornucopia of exploration. So this question that aliens exist gets back to the fact that when you look at just the stars in the Milky Way, scientists now know that many of those, not most of those stars have at least one planet, if not more, right? And there are billions of stars in the Milky Way. So there are billions and billions of planets in our galaxy alone. And then, of course, there's billions and billions of galaxies. So when you think just mathematically of how many possible worlds there are, it's impossible for us to say that there is some form of life out there, but it's also impossible for us to say that there is not, just because mathematically it just would seem impossible that there wouldn't be. However, one little interesting bit of spice to toss into that equation is that the universe is both unimaginably big, but also unimaginably old. At 14 billion years old, it's a lot of time. So how long does it take for life to form? Were we early? Were we late? Is it incredibly hard for life to form? Like, is it very, very difficult? Is just the percentage of all of those planets that exist out there that some of them might have life incredibly small? In which case, then if you add the salt of how soon life might form and the pepper of how big the universe is, it gives you this recipe of we just don't know. It could be that, sure, there's some other life form out there, but it's billions and billions of light years away, and we would never be able to detect that or visit that. So we'll just never know if they're there. So anyways, again, long answer to a very good question. I think personally, I'd be surprised if there wasn't some other kind of life form just because the math seems so incredible. So incredibly huge.
I'll keep going with these questions, Carol, unless I hear otherwise. Does that sound good?
Yeah, I did want to add another popular one that's coming up in the Q&A. Folks were curious whether the Chandra was involved in the Event Horizon project to have the first photo of a black hole.
Yes. So I guess I could share my browser really quick. Hold on. Pause share maybe. Boop. New share.
You might, if you are trying to share another window, you might need to stop sharing and then reshare if it's not working.
I did. Did that not work? Can you see?
Right now we're looking at your presentation.
All right, so it didn't work. I stopped sharing and then launched it again. Let me try again.
Okay.
All right, share again. Share. Can you see it now?
Yes, we do. Is
that working? Excellent.
All right, so I will say in my 20 plus years on the job, this was one of the most exciting days ever. I did know about this discovery a few weeks before it was released, and I was so excited to like talk about it with my husband and kids, and I contained myself. I kept quiet on it. I just kept hinting that something exciting was coming, but I behaved. And being able to just be even the tiniest part of this result was fascinating. And when I say tiny, I mean like microscopic level here. So yes, the EHT did this incredible job of essentially turning the Earth into a massive radio telescope to be able to observe the shadow of a black hole, if you will, because again, black holes are something that we can never see directly with human vision because they are so powerful. Their gravitational pull is so strong that nothing can escape them, not even light, right? So you can never see them directly, but you can see in this case the shadow or the eclipse, I guess you could call it, of the black hole, which is about as close as I think we could ever get. And Chandra was actually looking at the same object, M87, at the same time, because it's really important, as I mentioned earlier, having the entire universe of light, having this entire electromagnetic spectrum from radio waves all the way to gamma rays. It's really important. I mean, you can think about even just in our daily lives, like you're actually using different kinds of light all the time, right? So if you've ever heated up some macaroni and cheese in a microwave, you're using microwave light to disturb the water molecules of your food. If you're ever used a remote control to talk to your TV or something like that, you're using infrared light to speak between devices. If you've ever had a cavity or just a dentist appointment in general, you've had your dentist has used Xray light to essentially be able to see through the bone or the tooth essentially to where the cavity might be. So using light is really important, even just on Earth. So using light beyond Earth is also incredibly important. Being able to look at an object in multiple kinds of light is very important to be able to understand what's going on here. So the image that I have up on my screen on the right side is the very famous orange donut that the EHT produced. And this was just like, stopped my heart for a second the first time I saw it. It was so, so incredible. Chandra on the left looked at the same object at the same time and also over time. So Chandra has actually been looking at M87 for pretty much almost the entire time the telescope's been up. For over the course of 20 years, Chandra has looked at M87 quite a lot. And the point of having different telescopes is EHT zooming in and letting you see like that really close bird's eye view of what's happening right around the center of that black hole. A telescope like Chandra is showing you essentially that larger surrounding environment. So what that black hole is doing to the space around it, which tells you something different about it. So in this image, you can probably see, I don't know if you can see my cursor, but on the left image, there is this little yellow jet. That is a massive jet, a high energy emission that's coming out from that black hole, because though black holes, nothing can ever escape a black hole once it goes in. There are, of course, jets of material that are created, or jets of radiation that are created when material gets too close, but then is essentially popped out, if you will. So it's not anything that's going in and coming back out, but is as it's kind of like circling the drain, so to speak, before it goes all the way in. So anyways, this was really exciting to have any part of, because it was such a, I mean, for someone who does data visualization, being able to visualize a black hole, yeah, that was really one of the most exciting days like ever, job-wise, you know. So, all right, let me pop back over. Well, I guess I'll just leave it up on my screen.
Yeah, and Kim, I just wanted to let folks know that in the last 5 minutes, we are going to allow people to raise their hand, and we'll be able to take maybe 1 or 2 verbal questions. I'm so excited about the enthusiasm, both here in the emails that I got regarding questions and in the Q&A module. So yeah, it's great to see all the enthusiasm, and I want to make sure that everybody who had an opportunity to pose the question in the way they wanted to. So I'll kind of ping us at 5 of the hour, and we'll take a couple of hand raised questions if that's okay.
Sure, yeah, that sounds fantastic. So I guess looking at, well, there are still quite a few questions over here that I didn't get to. They're all such great questions. I feel bad having so many that I can't answer. I think I'll go over to this one. What if the sun explodes? Will we die? This is a great question. So our sun is fortunately a very boring, average kind of star. And what that means for us is that it will never explode because it's not big enough. So essentially, the fate of a star depends on its mass. And what that means is the more massive the star, the shorter the lifespan and the more exotic the ending, right? So if you have a very massive star, many, many times the mass of our sun, those stars live very short, powerful lives, and then they go out with a bang, like quite literally huge, huge bangs. So the more massive the star is, the more volatile its existence, right? Shorter lives, very powerful endings that are like incredible cosmic fireworks. The smaller the star is, and the sun is just kind of average, maybe slightly bit smaller than others, and still bigger than some. Just kind of middle-aged, mid-mass star, nothing exciting. But what that gives us is a very stable star. So our star is about halfway through its life right now. It's not quite 5 billion years old, and it'll probably live about another 5 billion years more. It will never explode because it's not massive enough, but in about 4 or 5 billion years, give or take, these timescales are not exact. Eventually, that star will essentially puff up a bit. It'll turn into a red giant phase, and when that happens, it'll engulf Mercury and Venus for sure, maybe Earth. But even if it doesn't engulf us, it'll be too close for comfort, and Earth will no longer be a hospital environment. And then after that, it'll kind of like puff off those outer layers and form what's called a planetary nebula. The name is kind of misleading. It has nothing to do with planets. It's just how they used to look to astronomers hundreds of years ago. And when that happens, it'll be very beautiful. Gorgeous for other people looking at us, but not so much for us. But again, this is like 5 billion years old. So please don't have any nightmares or anything like that. That happened to me once. I had a parent tell me that I'd given their children nightmares, and I was very apologetic and felt terrible about it. But I promise our star will not explode. So I think it's just really useful. The main takeaway is that stars live different lives based on how massive they are. And the really small stars, they're kind of, some of them are called failed stars. There are different kinds. There's like brown dwarfs, there's red dwarfs. Some of those stars can live for a really long time. So even though they're small and not terribly exciting, they actually have longevity on their side. And some of those stars, we have no idea how long they could last because the universe isn't old enough to tell us. They're still going, and we think they'll keep going for a really long time. So something to be said for slow and steady wins the race. Okay, so I'm not sure on timing, but let me go back to the other page really quick to see if there's any questions on there. What inspired you to use 3D visualizations and showcasing life and death of stars among other galactic matter? The science inspired me, right? There was a scientist, Tracy Delaney, who was at MIT that started doing this research in understanding the three-dimensionality of Cassie, but she didn't have any way to visualize that. So that was kind of like the turning point of this research for me, understanding that you can have 3D information, but when you can then take that 3D information and turn it into a visualization so you can understand it in a more visceral sense, that adds just a whole other layer of information. Can you predict when a star is about to die or when a star is about to be born? Yes, sort of. So we have this sort of general equation, right, that I was just talking about. The fate of a star depends on its mass. So you know approximately how long stars will live, for example, and what, if depending on how big they are, how volatile they are, what will happen to them, but not down to a very precise amount. So there is, for example, a star called Eta Carina. I can bring that up on my screen really quick. Eta Carina is likely a pair of stars, and hold on, let me just search Eta Carina. I like visuals. I can't really function without them, so you'll have to bear with me. Here we go. So Eta Carina is this beautiful nearby superstars. There's two of them kind of hunkered down inside this blue-white core. And the star's kind of getting old. And this will probably go supernova maybe sometime in our lifetimes, but that's like plus or minus maybe 500 years. So it's very hard to be perfectly precise with these types of time scales because human time scales are very different than star time scales. So we have a general sense of it. Supernova 1987A was a great example of seeing a star explode in near real time. I say real time, but of course it's Earth time, right? So Supernova 1987A is this guy right here, and it's actually outside our galaxy, and it's, I think, about 179,000 light years away. So though we saw it here in 1987, it had happened quite a long time before that because it had taken all of that time for the light to travel to us. However, seeing that star brighten and then seeing it change over time was also really incredible. I'll show you a very quick example of what it is we're seeing in real time because we have a time lapse of it. Here we go. So you can see the brightening on my screen, hopefully. That data is from 1999 until 2013. So we're just seeing a snippet of its lifetime. So being able to understand how these stars evolve over time is really important because, you know, we didn't really know exactly why when we looked at Supernova 1987A from the front, which is our view here on Earth, it kind of looks like a donut, right? But when you model it in 3D, you can see all of this material that kind of looks like a crown, right? Can you see that? And so the reason is in an earlier part of its lifetime, the star had burped up a ring of material, right? And then so when the star inside the center, when it exploded, that explosion rushed out and then heated up the ring of material and caused like these fingers of high energy radiation to appear. So that's how we're getting something that looks like this, which is very different than the view that we're getting when we just look at it face on like that.
So anyways, hopefully that answers that question. I think, Carol, did you want to move to live question or two, or are we at the point?
Yeah, let's go ahead, and if you have a question, go ahead and raise your hand. I see. There's a few folks that already knew this was coming. So, okay, Diego, you should be able to ask your question.
Yes. Hello. I'm in Cambodia right now, so it's right on the opposite side of the planet. The question is actually, I think it's one of the questions that was already highlighted as you were scrolling down your document with questions. And it's about one of the big things is the scale that we're learning and the size of things in the universe. And one of my students was asking a question, how long do you think is going to take for us to have the first selfie of, someone with the whole Milky Way in the background? And I want to give credit to CT for that question.
So I had loved that question in the list, which is why I highlighted it, because I really did want to get to it. So thank you for guessing that I wanted to answer that question. And I love that question because it's such a fun way to look at things, right? So
being able to visualize our world and our universe over time, it's improved so dramatically to me so quickly. When I feel like I'm always a kid and I'm always going to be this like young baby because I'm so used to thinking about and looking at data of these objects that are so incredibly old. So any human life, no matter the age of the human life, is just a blink in time because these ages are just so immense. And so when we look back to how we first started understanding our universe, when we first started looking up and recording data of it through cave paintings, for example, and then we moved on and we developed early telescopes, and people like Galileo looked up and did hand drawings of things like Saturn and the moon. And then later we developed these high-powered telescopes in order to look out at the universe, and we developed a space program that got us to the moon. And when we got to the moon, I think one of the most fascinating things about it was, yes, it was great to land on the moon, but really it was about looking back at Earth. It was the first time that we had had a human or two or three out of our planet far enough away to be able to look back and snap photos of what our entire planet, everybody who's ever lived, looked like, right? And that selfie moment was incredibly powerful. It quite literally launched an environmentalism act. And as we're actually getting to the 50th anniversary of Earth Day this month in April, I just had to sneak that in because I'm actually a huge fan of loving our planet and being as environmentally sustainable and conscious as you can. So I think the value of a selfie is not to be understated. Obviously, we know selfies of ourselves quite differently in like Instagram and Snapchat, but when you look back and you can take an Earth selfie, what a powerful moment. When we had the Voyager missions go out even farther and take a picture of essentially, Earth far, far, far away, or essentially just seeing the sun, just this little pale blue dot, that was yet another moment of showing how human exploration could impact how it is that we're feeling here on Earth. So I really look forward to the time when we could get out of our entire Milky Way and take a selfie of our cosmic home. This zip code that we have, this average star on a corner of one arm of the Milky Way, just an average spiral galaxy, is an incredibly important one because that's where all of human existence has ever been. So now we study our Milky Way galaxy by mostly looking at other similar spiral galaxies. To be able to get out of the Milky Way and actually image the entire Milky Way itself would be a very powerful scientific tool. It would give us a perspective that we just haven't been able to get so far. Right now we can see through the Milky Way, but there's always going to be material in between us and other things that we want to look at. We can never get that entire perspective. So the question that you asked, though, of when, is really hard because we've just gotten out of our solar system quite recently. Like, what was that, a year ago, I think, or maybe it was a little longer, but it's been very recently that we've gotten out of our solar system, and our solar system is just a little pinpoint in the entire Milky Way galaxy. So I cannot give an estimate as to when we'll be able to do it, but I can say your question is awesome because the fact that you're thinking of doing that at all is exactly the type of questions we need to be asking and exactly the type of technology we need to be developing to be able to do that and get there.
Any more live questions?
Yeah, so I want to be, we're right at the 8 o'clock hour, and I was wondering if it would be possible for us to take 2 more questions.
Sure, yeah.
Okay.
I'll try to keep them short. I'm not very good at that part.
That's okay. It's you're doing a great job. Okay, so Chiara, you should be able to ask your question.
Oh, okay. Wait, can you guys hear me? Okay. So
Indeed,
when you
yeah.
looked at Cassiopeia from Chandra, when you first discovered it, what was your initial reaction to seeing the star? And also, has there been any unpredicted changes in the 20 years of research of Cassiopeia?
That's a great question too. So, you're speaking near and dear to my heart because Cassiopeia is, as I think I mentioned in other talks, my favorite object in the universe, which is a kind of ridiculous thing to say because, there are so many objects in the universe, and it's also like picking your favorite child. You just shouldn't do it, and no one does. But I will say, for Chandra, let me go all the way back to 1999. So Chandra first looked at this object, Cassiopeia A, when, gosh, I think the telescope had only been open for a month. And we got this incredible data of Cassiopeia A right away. And I don't know if you can see my cursor, but right in the center of this image, there's a little tiny dot. That dot was the long-sought neutron star. So within weeks of Chandra launching, within days of Chandra opening its eyes and starting to take in this information, it had already seen something that previous telescopes had never been able to see, which was that when that star exploded, it left behind a very densely packed core that's called the neutron star. And that was just incredible to see. I think I have footage of the scientists in the control room when this data kind of first came in, and everybody's pointing at the screen and yelling excitedly because it not only showed that Chandra was operational and working well, but also how exciting it was to have such a momentous discovery so early on in the mission. And I didn't show it in my talk because I was trying to keep things short, but we've been observing Chandra on and off, Cassiopeia with Chandra on and off for now almost 21 years with Chandra. And so Cassiopeia is actually one of the calibration targets for Chandra, which means we use it to make sure the telescope's working well, which means we look at it over and over and over again. And it's also a very famous and popular object to study because it's just such a great example of a supernova that's near enough in our sky, that's not really blocked by a whole lot of material between it, that we can learn a lot about it. So you can see this is a very short time lapse that I'm looking at here, where you can see there are some green arrows that are showing that there's a shock wave around the perimeter, this high energy blue color that you're seeing here. That is the shock wave as the expansion of that remnant as it sweeps into outer space. But what's also occurring is a reverse shock. So you can see, you might want to go to this web page. I'll leave it up a little bit after, but you can see if you zoom into the video a little better that there's these little ripples that are going then backwards back into kind of the center of the star. So that is just one of many, many, many discoveries that scientists have been able to make about Cassiopeia A that I find exciting because it's like the gift that keeps on giving. Every time you think you know something about the star, you have 10 more questions. And I think that's why I like this field in general so much. Anytime we think we know something about our universe, you might get one answer and then 10 new questions open up, right? There's so much in our universe that we don't understand. So much of our universe isn't even in a type of light that we can observe. There's dark matter, there's dark energy, there's those are names of things that people literally don't understand what they are, and they make up most of our universe. So if you're the type of person that likes a lot of questions and a lot of puzzles, astronomy might very well be for you because there's always so many new questions to ask.
Thanks, Kim. So I think this is our last question. And I apologize to everybody in advance that we didn't get to everybody's questions. There's so much passion around this subject. So we really appreciate Kim joining us today. And I'm going to take a question from, I hope I'm pronouncing your name correctly, Ananya. You should be able to speak now.
So hi. In your opinion, out of all the different types of light in the electromagnetic spectrum, which one do you think is the most crucial or important to your displays and findings? What about the least important or crucial? Not saying that they're not crucial, but if you had to pick one.
That is a tough question to end with, and a really good one. I love that question because I really like talking about this idea of light and how important it is to look at all these different kinds of light in order to understand what's going on around us. And I mean that also not just in astronomy. That concept is not just for astronomy. It really is about anything. We use many different kinds of lights in areas of microscopy, in different areas of all sciences, essentially. Light is just one of the critical tools. But what's actually interesting is that it's not just light. In the past, again, 2 decades, we now understand that multi-messenger astronomy is also a really important thing. So going beyond light to things like gravitational waves, right? So there are all of these tools in the toolbox that I think are incredibly critical to use. Now, I work for Chandra, so if I didn't say X-ray light to your answer as being the most critical, I think I would get in trouble with everybody that I work with, so I have to say X-ray. But I will say that I'm very partial to X-rays in general anyways. There's something quite special about being able to understand the high energy universe, that world, the universe rather, of exploding stars and black holes and galaxies that smash into each other, and just all sorts of these amazingly energetic events that I find fascinating, that you really do need high energy material, high energy light in order to be able to understand. However, what I will add to that is X-ray astronomy is highly complementary to radio astronomy, which is the, quote, coolest type of light. Oh, coolest, not as in ooh, cool, but temperature-wise. I mean, not that they're not cool. But the idea of the opposite side of the spectrum being so complementary is, I think, a really fascinating thing. And let me just bring up a quick image to show you what I'm talking about. Here we go. That's one example, but here we go. I like this one better. So this is, for example, a galaxy with massive jets that are coming out of it. And this is called Cygnus A, and it's, 700 million light years away from us. Now look at this beauty. So what you're looking at here, the radio data that you're looking at is all the reddish kind of pink material. There are these cooler lobes around these jets of material. And the blue data is the X-ray data. So that's here's the core of the galaxy is right there in the middle. And there are all of these blue lobes of really hot gas around it with that cooler lobes of radio material coming out along the jets. So you can look at something like that, and you can look at it in a single light, right? You can look at it in optical light. Okay, beautiful. You can see the core of the galaxies right there. That's lovely. You can look at it only in X-ray light, and you can see those beautiful jets, and you can see those kind of cavities of material. You can look at it only in radio light, and you can see those lobes around the bipolar jets on either side. But really the power of this data set comes when you combine all three, right? So it really is the way those different kinds of light interact together to help give us the whole picture. So though I would have to say X-ray is my favorite, and I would definitely say radio is my second favorite, I don't know if I could say my least favorite. I'd feel really terrible. Maybe gamma rays, just because I don't really work with gamma rays that much, so I'll just toss them to the curb. But it's this idea of combining all of these different kinds of light to get that complete picture, that more full picture of what the universe is up to, that I think is really important. So yeah, I hope that answers your question, and I hope the other kinds of light weren't too offended.
Thanks, Kim. We really appreciate the way that you look out for the social emotional learning of all the different.
Yes, I try to be sensitive.
Thank you so much for joining us. this has been a great experience for our team and as well as our students in Southeast Asia and the Middle East and China. So we are going to, I think I had mentioned to all of the teachers that we have been recording this session and we'll be sharing it back so that you can kind of look at it a little bit more deeply. And I will take as a follow-up item, Kim, there's so many questions that we didn't get to answer. And so maybe we can find a way to kind of just pull together some resources where students that are really interested in investigating a little bit further can do so. And maybe I'll organize the questions and themes or something like that. And we'll share that back with the schools as a follow-up. Does that seem to make sense?
Yeah, if you create like a Google Doc with like the most popular questions, I'd be happy to answer those, and then for sure give web pages and other resources to look out for the other answers.
Great. All right. Thanks so much. Thanks everybody for joining us, and have a great evening or day, depending upon what part of the earth you're sitting on these days.
Bye, everyone. Keep looking up. The universe is yours.